All right, so then we're going to talk about section 3.2 and the derivative as a function. It seems like a broken record, right? We keep kind of talking about the same thing, and you're going to see that this is going to look exactly the same as what we did in section 3.1, the same thing as what we did in section 3.2, but the notation is going to be a little bit different. And here it says that we talked about the derivative at a point, x is equal to x sub 0, but now we're going to define the derivative as a function of each point of x instead of talking about a specific point and looking at it from a specific point. So here's our definition. And again, we're calling it a derivative now. So the derivative of a function f of x with respect to the variable x is the function f prime. It's kind of hard to see the prime on your sheet, but f prime whose value at x is the limit as h goes to 0 of f of x plus h minus f of x divided by h. The only thing different in here from our last section, what's like a little tiny thing that's different? The 0. So we're calling it x, any value of x, instead of a specific x sub 0, instead of a specific point. That's really the only thing different. We also have an alternative formula for the derivative, just like we did in chapter 2, where we can also say that it's the limit as z approaches x of f of z minus f of x divided by z minus x. So again, I can draw a picture similar to what we've done before. How's that for a picture? Not so good. Let's draw it on, I'll draw it on this screen here. It's a lot easier. So let me draw this. Let's say this is our function. So we have a point on this curve, and let's call that point x. And then we want another point on that curve that's going to be close to x, and let's call that point z. But we're saying we're taking x and we're just adding a little bit to it. We're adding h to it. So just like we were doing before, we're taking that point x and adding h to it. So we're saying that z is the same thing as x plus h. So that distance between x and z is really going to be h. And so if this is point P is going to be x sub 1 comma f of x sub 1. Not x sub 1, we're just calling it x, f of x. All right, and then we'll call this point q, and we're calling q z, comma f of z. And again, just like before, let's look at the secant slope. So let's look at the slope of the line that connects those 2 points. So the secant slope is, so the slope of that secant line from one point to the next point is going to be the change of our y values, f of z minus f of x. That's the change of our y values, this y value and this y value. So f of z minus f of x divided by the change of our x values, z minus x. So same concept that we've been dealing with for about 3 sections now. Yeah, P is this point, and P is on the graph of that curve, and it's also on the secant line that I drew. The secant line connects those 2 points. So it's on both of those. It's on the curve and the secant line. All right, so let's go back. Or let's just look on our notes where it says, let's calculate the derivatives from the definition. So we're going to use either one of the definitions up above, and then we're going to state the domain of each function and then find the derivatives. So the first one, A, is f of x is equal to the square root of x. So what is the domain of this function, and what does the graph of this function look like? Square root of x. What does square root function look like? Yeah, it goes from 0 to infinity. So square root of x looks like that. If we take in values of x, you can only use positive values of x, right? You can have the square root of 4, square root of 3, square root of 2, square root of 1. So the domain is going to be 0 to infinity. And now let's find the derivative. So we're calling the derivative f prime of x. And from our definition up above, it's going to be the limit as h goes to 0 of f of x plus h. So now we're just calling it x instead of x sub 0. We're not at a specific point x, but we're at just x. And this really is what we did in that last example that I had you guys work on too. We didn't have a specific point. We were coming up with that specific point. But we're going to do this the same way that we did before. We're going to take x plus h and plug it into our function for x. So we have the square root of x plus h minus f of x, so minus the square root of x, divided by h. And this is still a limit, so I still need to write limit in front of that. All right, so we can't take the limit of this because we can't just plug that 0 in because then we have a 0 in the denominator. So we have to do something in order to try to get a common factor of an h that we can maybe cancel out. And it has these radicals with subtraction. We can combine them. But what is something that we can try to do that we kind of did last week when we have those radicals? That was one of the tricks that we could do when we were finding one of those limits. But that was when we have a limit as something as x goes to infinity, where we have a numerator in the denominator, and we looked at the highest power of x in the denominator. So that was when we had something going to infinity, so specifically in that case. So we had another trick when we had radicals. There was one other trick, because that, go ahead. Yeah, we can multiply the top and the bottom by the conjugate of that radical term. So looking at the numerator, the conjugate is going to be so we have square root of x plus h minus square root of x. So we're going to multiply the bottom and the top by something. What's the conjugate of that? So the conjugate, instead of having subtraction, we're going to have addition. So it's going to be the same thing, but we're going to multiply by the square root of x plus h plus the square root of x. Okay. That's what the conjugate is going to be. So if we multiply the numerator by that, we have to multiply the denominator by that as well. Okay. So now let's do that multiplication. In the numerator, we're going to FOIL. In the denominator, we're going to keep it factored because the whole point is to try and cancel a common factor. So don't distribute that h into the denominator. So let's just keep the denominator factored. So don't distribute. All right, so this is the limit as h goes to 0. And now let's FOIL that numerator. What do we get when we multiply root x plus h times root x plus h? Just x plus h. Those square roots cancel. And then you see, since one is a sum and one is a difference of the same thing, inside and outside terms, what happens to them? They cancel, right? Because we have minus that root x times x plus h plus root x times x plus h, so they cancel. And then we have minus root x times root x. So it's just x, right? So it looks like it's going to be really complicated, but it makes it a lot easier when we do that, right? Seems like it's a big mess at first. Looks really messy, but it makes it a lot easier. And then the denominator, we're not doing anything with it. We're just leaving it h times square root of x plus h plus the square root of x. Now what happens? Yeah, these x's cancel and the h's cancel, right? You can cancel, after you cancel the x's, you can cancel the h's. And then we can take the limit as h goes to 0. What's in the numerator now? It's not nothing, it's not a 0, it's a 1. So we have 1 divided by the square root of x plus h plus the square root of x. So when we plug h When we plug 0 in for h, so what do you get when you plug 0 in for h? When you take that limit, you get 1 over square root of x plus square root of x. What's the square root of x plus the square root of x? So x plus x is 2x, so root x plus root x is 2 root x. So 1 over 2 root x. All right, so that's the derivative of that function. F of x is equal to the square root of x. So the derivative of that function is going to be 1 over 2 root x. All right, let me go on to a new page here. All right, then for b is f of x is equal to x plus the square root of x. So again, domain, this is going to be the same domain, 0 to infinity, because we have that square root of x. But go ahead and find this derivative on your own. Do the same thing that we did for this problem, exact same thing, and find the derivative of this one. All right, I have to warn you about kind of a double trick here, because when you plug in the x plus h into the function, you end up with this h plus square root of x plus h minus the square root of x. And trying to multiply this by the conjugate when you have 3 terms in there doesn't work. So let's do a little bit of this division first. Because this is division, we can do h divided by h plus x plus h divided by h. So we can separate this thing into 2 addition problems to make it easier when you take that conjugate. So you can write this instead as a limit as h goes to 0 of, now we're going to do h divided by h. So we're allowed to do that division plus, and then I'm going to write it as x plus h, square root of x plus h minus square root of x divided by h. So I can divide that as well. So we have square root of x plus h and then h plus h, of course, is going to be just 1. So and then you can think about this as 2 separate limits. The limits of one, the limit of this 1, and then the limit of that square root of x plus h minus square root of x divided by h. All right, then go ahead and finish this one and multiply, because you'll have to multiply the top and the bottom by the conjugate of that thing now. All right, so after we separate those 2 terms in that numerator, and we're multiplying by the conjugate, the 1 is fine, that just stays the 1. And now we have to FOIL. So we have x plus h times x plus h. That just becomes x plus h. And then the inside and the outside terms, they cancel. So we don't have to worry about what they are. How come, how what?
Here, you cannot just put this equation here. How can you put here?
Oh, yeah, you're right. This is not right. I have to multiply the top and the bottom by the same thing.
Yeah.
Thanks. Yeah, otherwise I'm changing the problem. So here I'm multiplying by the conjugate of the numerator, and I have to multiply the denominator by the same thing. Thanks. That wouldn't make sense. Plus square root of x, okay? That's better, right? So now multiplying that top, we FOIL that top, and then we have root x times root x. So that's just going to be minus x on the numerator. And the denominator of this part, we're just going to keep it, that big mess. H times square root of x plus h plus square root of x. Okay. And then the x's go away again in the numerator. So this is equal to the limit as h goes to 0. So the x's cancel, and we have 1 plus h over, keep that denominator factored, h times square root of x plus h plus square root of x. And these h's cancel. And now we have to take the limit. So we're going to take the limit, and that's going to be equal to 1 plus plugging h into that denominator, again, we have 1 over square root of x plus square root of x. So just like before, that's going to be equal to 1 plus 1 over 2 times the square root of x. So that's going to be our derivative. All right, then let's go to the next page and look at the next derivative. So let's differentiate this function. F of x is equal to x over x minus 1. So again, we're looking for the derivative, f prime of x, and we know it's going to be the limit as h goes to 0 of f of x plus h minus f of x divided by h. So this is the limit as h goes to 0. So now we need f of x plus h, so we're going to take x plus h, plug it into our function f, and when we do that we get x plus h over x plus h minus 1 minus, and now we're subtracting the function, so I have to write the function here, which is x over x minus 1, and we're going to divide that whole thing by h. So we have a complex fraction here, so in order to simplify this a little bit, I'm going to just take that 1 over h out. So the h is still in the denominator, but I just want one fraction in the numerator. So we're going to do that subtraction. We're going to combine those two terms with a subtraction. So we need a common denominator. So we have the x plus h minus 1, and then we have the x minus 1. So when we multiply those two things, that's what the common denominator is going to be. So let's write this as, we're starting with x plus h, and we know that we need to have the common denominator, which is going to be x plus h minus 1 times x minus 1. So we need to multiply the top by x minus 1 as well. So multiplying the bottom by x minus 1, got to multiply the top. All right, same thing with that second term. We're starting with x over x minus 1. That's what we're starting with. But we need the common denominator, so we need to multiply by x plus h minus 1. So we have to multiply the top by x plus h minus 1. All right, let's simplify this a little bit. We have the limit as h goes to 0, 1 over h. And let's FOIL the numerator here. We get x squared plus xh minus x minus h minus, and we have to distribute that x inside the parentheses, but since we have a minus, all the signs are going to change, so we just have to be careful with that. Distributing that x, we get x squared, and that's going to be minus x squared, and then we have minus xh, and then we have minus the negative x, so we have plus x that's left on the end after we distribute that minus x here, and then we have to divide that whole thing by that common denominator, x plus h minus 1 times x minus 1. Okay. And let's simplify. Limit as h goes to 0 of 1 over h. And when we look at the numerator, we see that the x squared is going to cancel, xh is going to cancel, and x is going to cancel. So the only thing that we're left with in the numerator after we cancel that is the minus h, and the denominator stays the same. Let's keep that as x plus h minus 1 times x minus 1. And we can cancel this h with this h, and we're just left with a negative 1 in the numerator. And now we're looking to see if we can take the limit by plugging 0 into that denominator for h. So when you plug 0 in for h, we have x minus 1 times x minus 1, and that ends up being x minus 1 squared. So that's going to be our derivative of that function x over x minus 1. All right, let's go back then to our notes. Yeah, let's take a look at the next part. It talks about notations here. So the derivative is going to be an operation that's performed on f of x. So one way that we write that is we say d dx. So it means that it's an operation that's performed on f of x. So we're finding d df, which means a derivative of that function f of x. And we also write it as f prime of x. So those mean the same thing. So we've already used f prime of x, but another way that we can write it is d dx of f of x. So all of these things that you see here, these are all the same notations. They mean the same thing. So you can write f prime of x, you can write y prime, you can write dy dx, means we're going to take the derivative of y with respect to x. We can take the df dx, derivative of the function f with respect to x, d dx of f of x. So all of those things there mean the same thing. So I'll use all of those kind of interchangeably. Maybe not all of them, but the first few definitely. All right, then let's look at differentiability, things that are differentiable on an interval, and one-sided derivatives. So a function f of x is differentiable on an open interval if it has a derivative at each point of the interval. So it's differentiable on a closed interval from a to b, if it's differentiable on the interior from a to b, and the limit as h approaches 0 from the right side, and the limit as h approaches 0 from the left side exist at the endpoints. So let's compute the left and the right-hand limits, the left and the right-hand derivatives, to see if the function below is going to be differentiable at p. So I'm going to go back to this page here, and I'm going to draw the function. So here's the function that we're going to use. So the first part of this line, this is going to be the function y is equal to x. So this point here is going to be 1, 1. And then after 1, our function is going to look like this. And now our function is going to be y is equal to 1 over x. Okay. So we have to look at the left and the right-hand limits of this function. So let's first look at the left-hand limits. So what we're doing is we're looking at the limit as h approaches 0 from the left-hand side of f of x plus h minus f of x divided by h, and that's equal to the limit as h approaches 0 from the left-hand side of, so when we're looking at the left-hand limit, the point that's going to be the potential problem is this point right here. So we have something funny going on here. This is actually going to be a cusp where something is changing at 1. So we want to see if the limit is going to be the same to the left of this point as it is going to be to the right of this point. So the 1 is going to be the problem. So really our x value that we're concerned with is x is equal to 1. That's our concern right here. So that's what our x is going to be. So 1 plus h minus f of 1. Everywhere else it's going to be fine. That's the only potential problem. All right, so now we have to take 1 plus h, and we're going to plug that into our function. So to the left of 1, we're looking at the function f of x is equal to x, or y is equal to x. So that's what we're plugging our 1 plus h into. And when we do that, we have 1 plus h minus f of 1. So we're looking at this function f of x is equal to x. So that's what we're plugging that 1 plus h into. So when we plug 1 into that function, we just get a 1 out as well. And divide that by h, and then we can see that we have limit as x approaches 0 from the left. It's going to be h over h, and that's going to be equal to 1. So our limit from the left-hand side, our derivative, the left-hand derivative is going to be equal to 1. And then let's go ahead and do the same thing for the right-hand derivative. So now we're looking at the limit as h goes to 0, h approaches 0 from the right-hand side. And we still have f of 1 plus h minus f of 1. So x is equal to 1 is still our potential problem. But now we're looking at our function. So if we look back at the previous page, the function from the right-hand side is going to be this function right here, where f of x is equal to 1 over x. So that's our new function right now. So we're taking 1 plus h and plugging it into that function. So this is equal to the limit as h approaches 0 from the right-hand side. And now we have 1 over 1 plus h, plugging that into our function. Oops, that's a little messy. So 1 plus h minus f of 1. If I plug a 1 into this function right here, we have 1 over 1, or just 1, and divide that all by h. So we can do the same thing. Again, we can try to simplify that numerator. We can do the subtraction, and we can pull out that 1 over h again if we want to. So let's get rid of this. And getting a common denominator then in the numerator, we have 1 over 1 plus h minus, and the common denominator needs to be 1 plus h. So we need to multiply the top and the bottom by 1 plus h. All right, then this is the limit as h goes to 0 from the right. And we have that 1 over h. And then inside the parentheses, if we do the subtraction, the denominator stays the same, and we subtract the numerators. So we have 1 minus h. So make sure to distribute that negative inside the parentheses. And then we have limit as h goes to 0 from the right, 1 over h. And then 1 minus 1, that's going to be 0. And we just have minus h divided by 1 plus h. The h's can cancel, and we're just left with a minus 1 then. So that's going to be minus 1 over 1 plus h. And then plugging in 0 from the right-hand side. So we can plug in a 0 here, and we get negative 1 divided by 1, and that's equal to a negative 1. So that's the derivative from the right-hand side. And we're going to say that since the left limit is not equal to the right limit, because the left one was positive 1, the right one is negative 1, the derivative of that function, f prime of 1, does not exist. And that was an example I said of a cusp in that function. And the derivative, when we have a cusp in a function, is always going to not exist. And that's the end of section 3.2.